All right, welcome everybody. My name is Martin Besner, and I'm the president and CTO at Staties. And I want to thank everybody for attending our crash course in Mixture Design of Experiments, or DOE. And this is a course that we do, or a webinar that we do 3 to 4 times a year. We do also have an advanced version of this that we do every so often as well. So I want to thank everybody for coming, and then we'll go ahead and get started. So just some preliminaries here. We do have a pretty decent sized group here. So to avoid distractions or somebody inadvertently leaving their microphone on and there being background noise, we did mute everybody. If you do have a question, you can post it in the question area in the GoToWebinar little widget. If I'm not able to get to it during the webinar, and I'll try to check it every so often, somebody from our team can get back to you via email. And if you do have any questions afterwards, for example, you realize, oh, something may have not been clear, you can feel free to email us at stathelp@staties.com. Just as a caveat, the slides as well as a recording of this webinar will be posted on the webinars page of our website, probably by the end of the day today, and it'll also be, this recording will also be on YouTube as well. So just some latest news from Staties. We do have, for those of you that are familiar with us, we do have 2 software products. We have Design Expert, which has been kind of our popular DOE software for the last 30 years. And then we do also have Staties 360, which was released just over a year ago. And we have actually a new version that was released just a couple weeks ago as well. And Design Expert also had a release, an update that was released at the same time. So if you're on a subscription or on a network license, you are eligible to upgrade for free. I will give a very small preview of this. Mostly, I'm just going to preview the features that are useful for mixture designs. I'm not going to go through every little thing that we put in there, but there are a couple things that are nice for those of you that are doing mixture DOE on a regular basis. Now, unfortunately, we only have about 45 minutes today to get through mixture DOE, which is not much. If you realize that, hey, maybe you'd like to go more in depth, you'd like some training with the software, you want something a little more full-fledged, we do have a live web mixture DOE workshop later in March. And this is instructor-led, it's interactive, it goes through the background, it also goes through software use. So if you take our 45-minute webinar and expand it to about 15 hours or so, that's pretty much what's going on there. So what are we going to be doing today? So let's go ahead and jump right into this. So first, big question is, what is a mixture experiment? Common question we always get is, do I need to do this as a mixture DOE, or can I use a Factorial Design or an RSM design? I'll talk a little bit about the different types of mixture designs. Then I'm going to go through some practical tips and tricks. So for those of you that may be intermediate experimenters who may have already done some mixture DOE, I do have some tips and tricks that I've collected over the past 10 plus years that I've been doing mixture DOE and helping people with mixture DOE. So hopefully you'll get something out of this. And then I'll wrap up and give you some pointers on if you want to continue studying this on your own, and some other resources that you can use to further your knowledge in this field. So let's go ahead and get right into this. So what is a mixture experiment? Okay, very important question. I always think it's actually easier to answer this by first showing you what a non-mixture experiment looks like. Having that example, I'll then show you how a mixture would be different from this. So I think it helps to set the stage here. So to keep, since we have people from a wide variety of fields and areas and whatnot here, I kept the examples a little bit simple so everybody can understand what's going on without having to have a deep knowledge in a bunch of different applications. So let's suppose we're baking a cake. And there are two things that we're interested in tweaking as part of this cake baking process. So we have the time, which we think should be somewhere between 20 and 30 minutes. And we have the temperature in the oven, which should be somewhere between 300 and 450 degrees Fahrenheit. Now, the response that we're interested in measuring is the moisture of the cake. So we might think that maybe perhaps if we, bake it at 30 minutes and 450 degrees Fahrenheit, it might be too dry. If we bake it at 20 minutes here and 300 degrees, it might be too moist still. It might not even be fully cooked. So we need to find some combination of time and temperature that gives us an acceptable moisture content in the cake. Now notice that in this experiment, both of our factors can be set independently of one another. So in other words, if we set time to 25 minutes, we can set the temperature anywhere between its range, 300 and 450 degrees Fahrenheit. Now this would be an example of a typical response surface experiment, or RSM. If you were only looking at the lows and highs, like 20 and 30 and 300 and 450 at those four combinations, then this would be a two-level factorial experiment. So this is an example response surface DOE that you may have seen. It looks something like this, where you have a column for time, you have a column for temperature, and you've got all these different combinations here. And if you go ahead and graphically kind of plot these points and take a look at what's going on here, you'll see that you're doing combinations here, and you're doing replicates, and you're doing a combination at these extremes here. So you're doing runs throughout this square kind of space here. Okay. So this is a very common example of something that I would say most people do on a regular basis that are doing DOE. Now, let's see how does a mixture experiment differ, and why do we care? Well, suppose we're deciding now, to keep it in the food realm, let's suppose we're deciding what cheese to put on a pizza. And what we're doing is we can blend 3 cheeses to make up the blend. We can mix 3 cheeses to make up the blend. We can put in mozzarella, we can put in provolone, or we can put in white cheddar, or we can put in one of them, or we can put in some combination of them. So we're going to try various combinations of the 3 cheeses, but the thing is that each pizza that we cook will be topped with a total of 6 ounces of cheese. So we don't want to go beyond 6 ounces. I mean, I would like to go beyond 6 ounces because that seems a little light for me, but for this example, this pizza manufacturer, this company is fixing it to be 6 ounces. And they're saying that mozzarella can go from 0 to 6 ounces, provolone can go from 0 to 6 ounces, and white cheddar can go from 0 to 6 ounces. Okay. So they can, if for example, notice that if you put in 6 ounces of mozzarella, you can't put in any provolone or white cheddar. So here is the key. This is what you need to look out for when you're doing this on your own. Notice that in this case, mozzarella plus provolone plus white cheddar has to total 6 ounces. So I could put in 6 ounces of one and 0 ounces of the other, or 3 of provolone, 3 of mozzarella, and leave the white cheddar out, and so on. Now the responses that we're measuring here are appearance, taste, texture, and of course the cost. Now notice that in this situation, now we're going to call these cheeses components because they're parts of a blend. These components cannot be set independently of one another. So if we put in 2 ounces of mozzarella cheese into the blend, we must put a total of 4 ounces of the other 2 cheeses into the blend. So the components have to sum up to a fixed total. And this is going to answer your question, do I have a mixture experiment or do I have a response surface or factorial experiment? If any of your columns in your spreadsheet, your design spreadsheet, add up equal a fixed total, you likely have a mixture. So a typical mixture DOE would look something like this. Notice how, for example, in this case, run number 1, I'm not putting in any mozzarella but I'm putting in 3 ounces of provolone and 3 ounces of white cheddar. Run number 2 is a mixture of the 3 blends here, which is mostly mozzarella. Notice that once again, if you go through and you add up each of these rows here, you'll see that they add up to 6. That is kind of at the heart of it, a mixture experiment. Now, if I go ahead and I take that spreadsheet and I look at the runs and I plot them in 3D space, I have 3 components, so I'm going to plot them in a cube. Notice how if you look at it here, you could actually see that these points all, I could almost put a piece of paper, flat piece of paper here, and all these points are going to be on that piece of paper. I don't have anything in the corner here, in the corner here. In fact, I could draw a triangle inside here that contains all of these points. So even though I have 3 components, they actually all fit in a 2-dimensional space here. And the reason for that is that I can only set 2 components independently. Once I set 2 of the cheeses, the 3rd cheese is automatically set to respect that 6-ounce mixture total. So what I'm going to do is now I'm going to flatten that triangle, and I'm going to take a look at what these runs look like. So notice how now my response, my design space is a triangle, and this is very common. Okay, it deals with the fact that we have components that cannot be set independently of one another. So whenever you look at these design spaces or graphs or contour plots, they're generally going to be fit within this triangle, or what we call a simplex technically. I have runs here at the vertices, which represent 1 cheese blends. I have some points here on the edges, which represent blends of 2 cheeses, and then I have points in the interior here, which represent blends of 3 cheeses. Okay. And notice how if I have a little number 2 here or something, that denotes a replicate, so that means that I should do that run independently twice. So just to wrap this up, blending experiments should usually be set up as a mixture DOE, with the caveat, but not always, okay? If you're varying like volume percent or weight percent, or you're adding up to a fixed total, it's generally going to be a mixture experiment. Now there are cases where you're blending stuff together and a mixture DOE might not be appropriate. So here's one example. If you're varying concentration, okay, or if you're varying the amounts of the components that you're putting in. So I'm putting in, basically I'm blending together the 3 cheeses, but I don't have an upper limit to them. Okay, I don't have a fixed total. Well, in that case, you may have a response surface or a factorial experiment. So you really need to look carefully for, is there an equal sign somewhere? With concentration, you generally don't have, when you're varying the concentration of 3 components, you generally don't have to have a sum in there. So the key, if there's one thing you're going to take home, it's that the key to verifying whether you need a mixture design is to determine if any of the columns in the design plan add up to a fixed total in each run. Now, just a little aside, this is something that we talk about in the advanced mixture webinar, is that you may have an experiment that's part a mixture. So for example, let's say you're baking a cake, you have a cake batter formulation, but then you may have non-mixture factors as well. So something like the temperature in the oven. So this would be called a mixture process design, and it's a little more complicated than just a mixture design. But at the heart, there's still a mixture there. And it's very common that you have a mixture and you're also processing it under various conditions, and the processing parameters may be interacting with the mixture formulation. So this would be a mixture process combined design. We unfortunately don't have time to talk about it now in this webinar, but we do talk about it in our advanced one and in the live web classes that we put on. So now let's look at some different types of mixture DOE that you may be using going forward now. And we'll also do one demo as well, just kind of go through a build and an analysis. Now, just as a disclaimer, really there's only one type of mixture DOE that I use 99% of the time, and that's what's called an optimal computer-generated design. But I'm still going to point out another type of design that you might run into once in a while. So there are really two basic categories of mixture DOEs. So there's simplex-based designs, and these are kind of what we call textbook designs or canned designs, meaning they're kind of pre-generated and you have to figure out if they're applicable to your problem or not. And then there's also optimal computer-generated designs, which go the other way, where you define your problem and then you tell the computer, build the best design for this situation. In practice, most of the designs I use, and by most I mean like 99% that I use, are these optimal computer-generated designs, because they're just so flexible compared to the simplex-based designs. But I will spend about 2 minutes, 3 minutes talking about the simplex-based designs, because you will see them every once in a while, and they do come in handy sometimes. So as I said, they're canned, they're straightforward, they're very easy to kind of get your head around. But in order to use a simplex design, one of the so this is a picture of a 3-component simplex design. It's kind of similar to the one that we saw before. This is a picture of a 4-component design, and notice how conveniently everything looks like a triangle or a simplex. If you want to use one of these designs, all the components must have ranges 0 to 100%, or a little more general is all the components must have the same range. So for example, A can go from 1 to 9, B can go from 2 to 10, and C can go from 21 to 30, meaning that when you look at the high minus low, it's 9. So essentially they all have the same range. So as I said, these are some examples of simplex designs here. And I think, these are incredibly restrictive and limited purpose. I mean, it rarely, it's not never, but it rarely makes sense for every component to go from 0 to 100% in the mixture. So for example, if you're making a bread dough, I mean, does it make sense for yeast to go from 0 to 100%, meaning you have a 100% yeast, a bread dough formulation that's 100% yeast? No, that doesn't make sense. Or if you're making, a cake, can you put in 100% butter or 100% flour? I mean, you'd never even consider those scenarios, because they're basically giving you useless information. And in my experience, it's also somewhat rare that out in nature all components have the same range. Now, that's not necessarily, as you saw in our cheese example, everything went from 0 to 6. Okay, so one of these must hold true. And here's a tip. Here's kind of an early tip. Don't force all your components to have the same range so that you can use a simplex design. I see this all the time. When I'm working with response surface designs, I often see people changing their problem so that they can use a central composite design. Every once in a while, I'll see somebody changing their mixture problem. They're essentially taking the problem and forcing it into this type of design, which I generally don't recommend. Better design, which we're going to talk about in just about 15 seconds here, is using an optimal computer-generated design. And in our software, both in Design Expert and Statis 360, if you're interested in using a simplex lattice design, it's found in the design tree under mixture. It's the first option there. Now, let's look at optimal design. This is a little bit more representative of what I would consider to be a real problem. It's still fairly simple. I kept it to 3 components just so that we can see the graphs very clearly and we can picture it. But this starts to get a little more realistic. So you might have 3 components. I'm just going to call them A, B, and C. Component A goes from 0 to 20%, B goes from 0 to 50%, and C goes from 0 to 50%. So they don't all have that. They don't go from 0 to 100. And this one has a range of 20, this one has a range of 50, this one has a range of 50. So I cannot use any design based on a simplex unless I change my bounds, which I shouldn't be doing that, because my bounds are supposed to be based on scientific knowledge. However, I also have a multi-component constraint here, which says that A plus B must be at least 10%. So I can't have A and B at 0. The sum of them must be at least 10%. And next, I also have what I call a ratio constraint, meaning the ratio of B to C must be between 1 and 1.5. So in other words, I can't have 100 times more B in the mixture than I have C. In other words, B and C need to be roughly in the same proportion, or I could have maybe a little more B, 50% more B than C in my mixture here. So I can't have a situation where C is at 50% and B is at 1%, because that would be a ratio of 50. My ratio at most can be 1.5. And finally, I have an equality constraint, which is A plus B plus C equals 100% here. Now, this is what the design space looks like. This is the full 0 to 100% simplex. This white space here, this white space here is all of the points in this triangle here, in this simplex here, that satisfy all those constraints that I put on. Okay, so you can notice that A, it's a 5-sided Strangler, 1, 2, 3. It's a 4-sided figure, but it's kind of a really strange polygon. And it only really covers a small percent of the entire 0 to 100% space. And this little triangle here is basically the smallest simplex here that fully contains this white region. Okay. So that's where we're at. Notice how this is not a great candidate for a simplex lattice design. If I wanted to do a simplex lattice design, I'd have to somehow force a triangle here. So what I'm going to do is I'm going to magnify this space now and zoom in and look at this. So this gives me a little more resolution here. Now here's what an optimal computer generated design would look like if you use Design Expert or Statis 360. Here's the original space, and I would put in some parameters. I would put in some how many runs I want, and I would get something that looks like this, where the red dots represent runs. And I get some replicates here. I get some points on the interior. I get some points along the edges and vertices. So notice how, and I'll talk about this in just a second on how this is done, but you can notice here that the software will automatically fill the space with what it thinks is the best or optimal design. So if I really wanted to use a simplex lattice design, I'd either have to, just do this, or I'd have to, basically find some triangle or simplex that I thought was acceptable, which is not a good idea. Now, optimal designs are actually straightforward to build, and really all the steps is first, and I'm going to go through an example of this in just a second, is first you choose your components. Okay, let me just move this little widget out of the way here. So first you choose the components, and this is done using scientific knowledge or your background on the process that you're working with. Set their lower and upper bounds, and add any constraints that involve more than one component. So it seems simple enough. So here's a screenshot of that. You choose how many components you have. You set their total. Now notice how if you didn't have this here, it would be a response surface design. But because you have a total here, it's a mixture design. And then you go ahead and put in the names and the lows and the highs of all your components here. And then finally put in any ratio constraints or sum constraints, or basically any of these types of constraints here would go in this edit constraints button. Afterwards, you need to choose the design size, what types of runs will go in the design, how many blocks you need, what model order you're interested in estimating, and so on. So this is basically what you need to specify. So you're specifying what types of runs do you want. For example, how many replicates do you want? How many lack of fit points do you want? Unfortunately, because we only have 45 minutes, we really don't have much time to go into all these details here, but in our advanced mixture webinar, we go through what all of these mean and how many should I choose, and if I want to add more, where should I add them, and so on. So what I'm going to do now is just switch over to our software just to show you a quick example of how to build this and analyze and optimize this as well. Okay, this is going to be a very quick 3 to 4 minute example, so we can't get into too much detail, but hopefully you should at least see what the process looks like after this. And I'm going to go back and use this pizza cheese blend example and use the following components. So I have 3 components. Mozzarella goes from 2 to 6 ounces, provolone goes from 1 to 4 ounces, and white cheddar goes from 0 to 2 ounces, with the total amount of cheese being 6 ounces. Okay, so let me go ahead and switch over to the software here. Okay, so what I would do is I would go to New Design, I would go to Mixture, I would go to Optimal. If you try building this as a simplex lattice, the software will complain. It will say you don't have a space that looks like a simplex. So what I'm going to do is I'm going to put in a total of 6 ounces. First component is going to be mozzarella, which goes from 2 to 5. Provolone, which goes from 1 through 4. And then white cheddar, which goes from 0 to 2. Okay. If I had any constraints involving more than one component, I click on this Edit Constraints button. Then if I go to Next, I'm just going to stick with the defaults for now. So 16, it's, Design Expert or Statis 360 will suggest 16 runs here. We could spend the whole 45 minutes just talking about this screen, but I'm just going to go ahead and stick with the defaults here, meaning I have to basically test 16 pizzas. And now I would put in our responses. Now I think that there were 4 responses, but they were only interested in measuring the texture. So whether it was gooey or whether it was basically the feel, the mouth feel of the pizza. So I'm going to go ahead and click Finish here and go ahead. It's going to go ahead and build the design, and there we go. I just got a question about, can you visualize the design space before you collect the data? And the answer is yes. You can go to the evaluation, and if you go to the graphs here, you can see what the contour plot looks like here, and you can also see the real contour. So this is in the 0 to 100 space. So you can see that if I were to go from 0 to 100% for all my components, I would be in this gray simplex here. But this white region here is the region that satisfies all those constraints that I had put in. Just as a warning, once you get beyond like 4 components, visualizing this starts to become a little tedious because I can only look at 3 components or 4 components at a time. So so beyond 3 or 4 components, it starts to become a little tedious to do this. Okay. What I'm going to do is, we used to get questions all the time, people saying, hey, you know what, I can't measure out 3.44174 ounces of mozzarella cheese. I can't measure out, and I'm going to make this a little bigger, so Control plus mouse wheel. I can't measure out 0.0133597 ounces of white cheddar. So what I'm going to do is I'm going to use this round columns feature that's new in our software, and I'm going to round this off to, let's say, 2 decimal places. Now, you could round this off by hand, but the problem is if you round, because everything has to sum up to 6, if you round something one way, you have to figure out how to round the other things, and there's often more than one way to round that makes sense. So what our software will do is it'll actually go ahead and try to find the optimal rounding. It'll try to round it off to the closest point near your original point that's at 2 decimal places. So I'm going to go ahead and click OK. It's going to give me a warning, and I get something that looks like this. So a little bit easier. So I could probably measure out to 2 decimal places if I'm looking at ounces. Okay. So now what I'm going to go ahead and what I'm going to do is I'm just going to open up a data file that already has my responses in there. Okay, so this one was rounded off to 1 decimal point, which is probably fine. I mean, practically speaking, 3.8 versus 3.9 ounces of mozzarella cheese is, I mean, I'm not a food scientist by training, but I would guess based on common sense, it's not going to make that much of a difference. So I'm going to go ahead and analyze this now. I'm going to call this the taste analysis here. I'm going to go ahead and start the analysis. I'm sorry, let's make this a little smaller. It's suggesting a quadratic model, so meaning a model that has some curvature in it. And again, I really wish I could spend a lot more time on this, but at the end of the day, what we care about is we care about this graph here. Okay, so if I'm trying to look at where am I getting the best taste, it's going to be somewhere in this region here. Okay, so somewhere, you know, if you look down this way, white kind of looks like it's in the direction of lots of white cheddar. I can also use the numerical optimization here and try to maximize the taste as well. See, let the computer figure out the solution for me. And if I look at this, it looks like it's going to be somewhere, yeah, somewhere right around here. Okay, I could look at a 3D surface as well. Let's look at the taste. So if I look at a 3D surface, so it looks like it's somewhere around here at this edge. Okay. So as I said, unfortunately, that's really all we have time to go through today on this demo, but feel free to sign up for our next free webinar if you want to go through a lot more detail and less of the background. So I'm going to go ahead and close this. I'm not going to go ahead and save the changes, and I'm just going to go ahead and go back now to the tips and the tricks part. So this is a very, in my opinion, it's my favorite section here. So here are just a few tips and tricks to help you get started with mixture DOEs. Now I'm going to go through each of these in a little bit of detail, but the first one is don't use factorial designs. Second one, don't convert to ratios so that you can use response surface designs. Number three is spend a lot of time choosing the components and their ranges. Kind of a hint here, most of the failures I see in mixture DOE is not due to choosing the wrong design or making a mistake in the analysis. It's due to the fact that you chose your components incorrectly, or you chose their ranges, like their lows and their highs. You know, I don't want to say incorrectly, but maybe you didn't quite get to the sweet spot. You didn't quite choose a design space that encapsulates the response you're looking for. Experiment iteratively, especially when you're dealing with a new problem. And the fifth one is master building these optimal designs. So let's go through all of these now in a little bit of detail. First one, and I don't know why this happens, but every time I read a book, like a textbook on mixture DOE, they always start with, oh, here's how you can use a factorial design to do mixture DOE. And it's very limited purpose and it's very suboptimal in my opinion, but it seems to never be going away. So here's what the argument is. Well, let's say you have 4 components, A, B, C, and D. Components A, B, and C go from 0 to 10%. And component D is what we call like a filler, meaning the only reason it's in the mixture is to bring the volume or the weight up to some fixed total. So basically fill. So like usually it's water or something inert, quote unquote. Now, what textbooks will often suggest is that you should ignore, or you can ignore D because you don't care about it, and performing a 2 to the 3 factorial design on components A, B, and C. Okay. Now, in my opinion, and in my experience, this approach has 2 major issues, and I'm really not sure why it's still being even suggested. Well, first of all, the design that you get is poor. It only looks at the extremes of the factor ranges. So you're only considering 0 and 10%. You're not going to be looking at what happens if B is at 7% or B is at 1.5%. Second of all, if it turns out that that one component you think is a filler, so component D, if component D is actually has some active effect that's driving your response that you're measuring, the model that you get, the predictive model, is going to be misleading. What you see on the ANOVA as component A might actually be some blend of component A and D. You get aliasing. So let's look at an example. Here is what that, maybe I should have swapped these, but a factorial design ignoring D looks like this. It's 8 runs and everything is at 0 or 10%. Here is what a 4-component optimal design looks like. notice how it has 10 runs, so it has 2 more runs. It now has component D that's actually as part of your experiment. And notice how it's looking at, lots of runs, lots of interesting runs. Ones where component A is at 3.6, component B here is at 5.5. You have blends of all three. And in fact, in the factorial design, I mean, does it make sense to do a run where it's 100% filler? Here, you're always going to get that run where everything is at its low point. So maybe that run may not even make sense. And if that run doesn't make sense, then you can't use this. You can't even use this approach. So notice how if you fit a model here to this factorial approach, you're only going to be able to get a flat plane. There's not going to be any curvature. There's not going to be any information about interactions or any nonlinear blending effects. But you get all of that with this optimal design up here. You get, you're able to identify if any components are blending non-linearly. You're able to detect any optimal formulations that occur in the middle of the space or occur halfway along an edge of the space. So really, to me, I'm not sure why this approach is still promoted. I mean, you can make the argument that you could use it for screening, but even then, there are mixture screening designs that are optimal designs that are, in my opinion, better. And notice how you have to have a filler component. So if it turns out that A, B, and C, the sum of their upper components, the upper bounds might be above 100%, you can't even use this. So this is only used in a small number of problems, and it's a suboptimal approach. And there might be many cases where this doesn't apply to your work. So my opinion is just ignore it. Now, the second one that's somewhat related is don't use ratios so that you can use a factorial or response surface design. I see this very commonly, and I see this with, some statisticians even. I've seen this. I have no idea why, but I've seen some statisticians say, you know what, I don't want to learn mixture Dewey. Let's convert everything to ratios so that we can use a central composite design, for example. So here's what the setup looks like. Well, first of all, let's say you have 3 components, A, B, and C. What I've seen people do is say, you know what, I'm going to take 2 ratios. I'm going to look at the ratio of A to C and the ratio of B to C. Okay, now I have 2 components that, or I don't want to say 2 components, but 2 ratios that don't have a fixed total anymore. And I can use my, I could use a central composite design here. Well, first of all, you can't use this if A, B, and C have a lower bound of 0. So chances are you might be running into a problem in the future where this doesn't work. So I don't see it as a good excuse to avoid using mixtures. And in my experience, this is usually a bad idea. This produces poor designs in the original mixture space. So what ends up happening is that people will convert mixture components to ratios, then they'll take the ratios and do a response surface design. But because the ratios, the scaling is a little weird, when you map the ratio design back to the original mixture space, sometimes you get these really weird wonky designs because the midpoint between along a component's range is not necessarily correspond with the midpoint along on the ratio. I also find this to be tedious. It requires converting between percentages and ratios, and once again, I don't like it because it may produce models that are misleading. Now a caveat here is, if you're doing a problem where you really care about the ratios, meaning you think the ratios are driving the response, and it makes sense naturally, kind of, scientifically or from an engineering point of view to look at ratios, then it's perfectly fine to use ratios. What I'm just talking about is people who are converting something that's a clear-cut problem of proportions or volume percent or weight percent and converting it to a ratio and then back converting to a mixture. So I don't want to, harp on this too hard, but there are cases, there's a caveat that if ratios really are what you care about and they're driving the underlying process, then it's fine. But if you have a component that so I mean, I don't really have to say much more about that. We have some great pictures on where this fails. Unfortunately, again, we're a little short on time, so we're gonna have to just move on here. Now, I do have an interesting comment here that somebody said that, let's see here, I just saw it come in. Let's see here, I want to get to some of these. Black belt training only trains Factorial Designs, so since that is all they know, they use it everywhere and for everything. Yeah, I agree. I think, I think that's a shame, but it is, it's why we try to promote that with these webinars here, because we'd rather have people doing this stuff correctly. Now, this is probably the one I think is most important, is spend a lot of time choosing the components and the ranges. The first step in any mixture experiment is choosing what components to blend and what the upper and lower bounds of each component will be, right? Now, this step is critical. Most of the quote unquote failures I've seen are not due to somebody choosing a 14 run design instead of a 16 run design, or a cubic model instead of a quadratic model. It's usually due to choosing the wrong mixture components and or the wrong bounds. Okay. Now, components and their bounds are usually chosen using science, subject matter knowledge, historical data, educated guesses, and so on. And of course, the tricky thing is with mixture DOE is if you put in more of one component, you have to take, you have to let some of the other components be put in smaller quantities in the mixture. So it's all kind of this, it's all dependent on one another. And here's what ends up happening usually. So I like to call this the simplex of truth, meaning if I knew the truth, like if I had the answer in the back of the textbook, this is what this triangle looks like here. Okay. And my goal is to try to get into that sweet spot. But what ends up happening sometimes is people instead, they experiment here. So they set their experiment up here, collect their data, analyze, and they get a flat surface that says that everything is the same. Any of your formulations will be expected to give you roughly the same response. When in reality, of course, we don't know this, but when in reality, what we should have done is maybe we should have had a design that looked something like this, where we could have had a chance to detect this edge here, this red area in the edge here. So again, it's really figuring out where to experiment. That in my experience, that's where 90% of the success comes from, is getting those bounds correct. Now, this ties into my next tip, which is, you might not get that, you might not get the region correct on the first step, but maybe if you don't use your entire run budget immediately, maybe you can do some additional follow-up runs in a region of interest. So let's take a look at this next tip. So consider an iterative approach. And once again, design of experiments textbooks, even up to the PhD level, down to the level that are more geared towards engineers and biologists and chemists and whatnot, they almost often present DOE as a one-shot approach, meaning you have your design space, you have a budget of 22 runs, you do 22 runs, you analyze the data, and that's it. Okay, that's basically the way that DOE is almost always presented. And in my experience, this is fine, but in other cases it can be wasteful, because if you use up all the runs that you have, you use up all your raw materials, or you use up or whatever, you use up all your run budget, you don't have any chance to pivot. So instead of depleting your entire run budget on the first pass of the experiment, maybe consider using a fraction of the runs and leave some behind, kind of as backup. Of course, this assumes that you have a few extra runs you can maybe set aside for later. If you're at the bare minimum already, well, I mean, this might not be, this might not work. But maybe you can only, if you have a run budget that's somewhat reasonable, maybe you can do 80% of your runs and then look at the results and then figure out where do you want to put in the other 20% of your runs. Maybe you want to expand the mixture space and put the remaining runs in a new area to better optimize the process. Maybe it turns out that your original design space was way too big and there's a little tiny area of interest, and you want to put your runs near that tiny area of interest to get kind of more resolution and precision in that area. Maybe you fit a quadratic model, but you really wanted to, it turns out that you should be fitting a cubic model. Maybe it turns out that everything is great and you just want to fill in some big gaps in the space just to kind of make sure there's nothing crazy going on. There's a million things you can do depending on what the results from your first experiment look like. So again, there's a webinar on our YouTube channel that talks about this, talks about expanding the space, shrinking the space, going up a higher order model. Sometimes you might botch a sample and you might need to redo a run. Maybe you want to add more replicates. Maybe you're getting strange results and you want to repeat a couple of the points a few times just to make sure that there wasn't some measurement error or something didn't go wrong. If you use up your entire run budget on the first pass through, you're never going to get it. You're not going to get a chance to answer these questions. So, and we do have, this is that sequential experimentation video I was talking about, and in Statis 360 and in Design Expert, we do have now new features called Augment Design. So that's basically if you want to continue on with your design and add more runs without throwing away the original design. So basically like building on a design. And finally, the last tip, and I'm sorry we're getting close to the end here, is really spend some time on on mastering these optimal computer generated designs. Most of the designs you'll probably deal with will be these optimal designs, and learning the ins and outs. So taking 30 to 60 minutes to learn the basics, I think that's going to pay huge dividends going forward. And here are some three resources you can use. And as I said, there is an advanced version of this webinar. I did it sometime last year, and it's available on our YouTube channel. So if you don't want to wait till the next time that we do it live, you can go ahead and see the old one, which is not that these don't change that much every time we do them. There are some small tweaks and updates, but if you want to get a head start, you can feel free to check out what we have on our YouTube channel. So let's go ahead and get to the conclusion here. So Mixture DOE, very powerful tool that unfortunately doesn't receive much attention. Design Expert and Statis 360 software contains all the latest and greatest tools for building and analyzing mixture experiments. And the key to recognizing a mixture experiment is determining if there is an equality constraint. So if you enjoyed this presentation and found it useful, consider taking our 4-day workshop that dives into all these details, all these things that I discussed, and way more. I mean, they spend 4 half days on what I spent 45 minutes on. Here are some references. So this is a very technical textbook. I generally don't recommend it unless you're like a statistician with a master's degree. This book is more geared towards engineers here. And this, of course, is our little ad for our workshop here. So I'm just going to give a quick preview of Statis 360, kind of some of the new features here. So this ends the main portion of the presentation, but I want to go through and just look at the mixture, the relevant features to Mixture DOE. So the first one is the Modified Design Space Wizard. So that's for iterative experimentation, round columns, and then Python scripting as well. So the first one, I talked about this, and I'm going to just spend about 30 seconds on each of these. Is let's say you do your experiment and you realize, oh, maybe your design space should have been bigger, or you want to shrink it going forward, or you want to shift it over. We do have a Modified Design Space Wizard that basically does it automatically for you. You just walk through the steps, tell the wizard your run budget and whatnot, and go from there. We also have this round columns feature that I actually used as part of this presentation. Okay, so if you want to automatically round off to a desired level of precision, you can go ahead and use that. And finally, we have Python scripting. So if you have Statis 360, which is our, kind of our Design Expert Pro, there's a button here called Script Editor, and you can actually use Python to write your own scripts to do things like automating routine processes or creating simulations. Now, this is somewhat more of an intermediate to advanced feature. Combine features of Statis 360 with features from relevant Python packages, create infinitely customizable plots and graphs, And finally, facilitate the import and export of data between Statics 360 and other software. Okay, so if you're using our software and you want to take the design spreadsheet that's generated and send it to another software and then put it back in Design Expert, Python scripting can do that automatically for you. So I want to thank everybody for joining. Thank everybody for listening. Hopefully you got something out of this and enjoyed this presentation. So my personal email is here if you want to reach out to me. And yeah, and we hope that you join us for another one of these webinars going forward, especially the advanced mixed one. If you liked this one, we're going to go through a lot more detail, things like how to really build these optimal designs, mixture process designs, more tips and tricks, and so on. So I want to wish everybody a good day or good morning or good evening, depending on where you are. And thanks again, and hope to see you soon. And then we wish you the best of luck. Thank you now.